So we might see some videos on that. We've got a couple more we can watch. All right, next I want to talk about secondary waves. And secondary waves are the second fastest. And they move perpendicular to the wave. Okay, so secondary waves move perpendicular to the wave. So what kind of models for you here? In the P wave, if you watch that point, so you can see in the primary waves how that blue dot moves back and forth. On the secondary wave, you see the waves do move in that direction, but what does the secondary wave do to the point?
Up and down.
It's go up and down. So that's the big thing about the secondary. Then the surface waves. These are very localized waves. They're not really going to travel all the way across the globe. The only ones that move across the world are primary and secondary. The surface waves are by far the most destructive waves out of the two. And that's because not only are you now being pushed in the same directions, way back and forth, and up and down, but surface waves move side to side. Now, if you can try and envision this, being a building, and simultaneously getting pushed back and forth, up and down, and side to side, chances are you're not going to last. Okay, and when we look at a lot of the buildings that were built in California, especially during the gold rush in the early 1900s, it's a lot of brick. And if one thing we've learned about brick over the years, it is not very forgiving. It doesn't bend easy. It doesn't take stress easy. And so when we get earthquakes, we typically get a lot of destruction in major cities because of their stone construction. When we look at some of the major cities around the world who have absolutely devastating effects because of earthquakes, it's where you have extremely crowded populations, so of course you're going to have a lot of death. But you also don't have strong building codes. When you allow 40 people to live in a tiny metal shack on a hill that is made of very loose soil, when you get an earthquake, that soil gives way, and there goes the entire town. And you're going to lose a lot of people.
So is that all you want us to know? Switch waves, side to side.
One more thing I do need you guys to know is, and you will see this diagram if you look inside your textbook, if we have an earthquake here at the surface, I'll be drawing our outer and inner core. One thing I want you guys to notice is that when the waves come out, what happened here within the mantle? Did it go straight down?
No.
So what happened? It gets bent. That's because the waves change speed and direction when they travel through new material. Alright, what I want you guys to do is find that diagram in the book. So you guys got your laptops, find the diagram in your book. In this diagram, you'll notice that you have all these lines that are coming down from the epicenter. And then what you notice when it's going through the layers, it hits the outer core, and it does what? Changes its direction again. Now, remember we talked about the fact that we think that our inner core is solid, 80% iron, 20% nickel, and we think the outer core is liquid? As far as I know, we asked, how do we know that? Well, this is how we know that. That concept of what the interior of the Earth was completely non-existent in our minds until the late 60s. In fact, the concept of seismology was accidental, as usual.
How was it accidental?
Because we didn't set up seismometers to measure earthquakes, we set them up to see who was testing atomic weapons.
Really?
Yeah. One of the first stages to developing atomic weapons is an underground explosion test.
So they dug a hole and blew a bomb.
Yeah.
Just to see the waves on the ground.
Well, and by doing that, that releases seismic waves. And therefore, we set up all these monitors throughout the world to see who is letting off these seismic.
Or since when really do they sound or they like?
No, it's literally the particles moving of rock.
So it's literally something that you doesn't see it.
Yep.
So has it actually 100% been proven that the Earth is 80% liquid and iron and
Whether the percentages are correct, we don't know. But yes, based on the way that the waves move, the speed at which they change, and the way that they are bent in their direction, tells us that you go from a liquid in the outer core to a solid inner core. That we do know. One of the things that's also really important from this diagram, as you guys will notice, that one of the waves does not enter the core. Which wave does not enter the core? Say again? The S waves. What are S waves called? Secondary. Okay, so a lot of times the P wave, if you guys remember that, P wave is primary, and S wave is your secondary. S waves do not enter the core. So S waves will not enter the core. They just simply don't have the strength to make it through the core.
What are S waves?
Secondary. P waves are primary, S is secondary.
Don't make it through the core.
Yep. Now, one of the things that's kind of neat is you might have asked yourself, how do they know where that earthquake occurred? You ever asked yourself that? Hey, this earthquake, so, out in the middle of the ocean, you're like, okay, there's nobody in the middle of the ocean. Tell me that earthquake just occurred there. How do we know that's where the earthquake occurred? Well, that's why we're going to do a quick little lab with you guys. You're going to have to use a little bit of math for me. I know, but oh well. So we're going to do a little bit of a lab that'll help you understand how we actually use seismometers to then determine where the earthquake occurred. So it's kind of a neat little tool. So let's go ahead and get you guys into your groups.